Hello, my name is Sufyan Ben Daoud. I'm the Precision Analog Business Development Manager here at TI Silicon Valley. And for this session, I'm going to be talking to you about the impact of the signal chain, really optimizing your SAR ADC design. Oftentimes, our applications engineers get questions ranging from the ADC not performing up to spec. Each application obviously gets a unique set of design goals. For that, you really need to analyze the signal chain and consider the trade-offs. For example, as far as trade-offs go, if you optimize your SAR ADC design for one aspect, meaning low power, for example, for that matter, you're likely to lose on the noise. In other words, the noise floor raises up as a result of lowering your power budget. Another example is, in terms of analyzing the signal chain, estimating the noise performance, be it pertaining to voltage noise, current noise, densities, peak-to-peak, etc. Calculation of the power budget. And again, I say each application sets a unique goal because really it depends on whether we're talking about DC performance or AC performance. In other words, the DC precision or the AC performance, such as speed and the like. For this session, I'm going to introduce you to something we call TI Precision Designs. This is particular to SAR ADCs, but it goes beyond ADCs, obviously. There are currently 4 designs that feature the ADS 8881. That's the ADS 8881, which is TI's newest 18-bit 1 megasample per second ADC. That's a SAR ADC. It's a SAR architecture. This is really a systematic approach to designing SAR ADCs. It's a complete reference design that has the theory, calculations, simulations, and the validation as well. And last but not least, these are verified, certified, prototyped, and completely tested for your convenience. So the 4 design optimizations for this particular device, namely the ADS 8881 that we'll be talking throughout the presentation today, are as follows. Number 1, it would be the 1 microsecond full-scale step response. And for that, we've chosen a few components that we'll share the details on later, something like an OPA 2350. We've also targeted a lowest distortion and noise at 1 megasamples per second, namely the sampling speed of the A to D. And for that, we've chosen another component called the THS 4521. This is as the input amplifier, a reference as well called the Ref 5045, among other devices that we'll touch on later. Then we've chosen to go with the lowest power at 1 megasamples per second. Clearly, that's a trade-off of the preceding one. The OPA 2320 is the input amplifier for this one. And then a 1.6 megahertz anti-aliasing filter, along with some other references and high-speed devices also. And then finally, the last one would be an ultra-low power design at 10 kilosamples per second. So you'll notice that we basically went down in speed. So as opposed to 1 megasamples per second, we're now talking about 10 kilosamples per second. And for that, we've chosen, again, selected parts that will achieve that lowest power available to us. In terms of performance comparison, and this is really what it comes in handy in terms of understanding the trade-offs, what you can see from the chart here is that if you target the 1 microsecond step response, as we said earlier, your effective number bit is about 18. That's your effective resolution, essentially. Your ENOB is not ideal. It's about 15.5, so not outstanding. There's certainly better than that. Your SNR, somewhere around 95 dB or so. The linearity, however, is absolutely superb, as is the response time. Clearly, that's what we're designed for. We designed for the response time, and so we do get an excellent response time. If we go on to the second one, lowest distortion and noise at 1 megasamples per second, clearly the power goes down here a little bit, so 40 milliwatts, 16 ENOB, 99 dB of SNR, which is much better than what we had in the previous case. Excellent linearity, but not as good a response time. All right, so that is the trade-off, and so on and so forth. If we go to lowest power, clearly we're going to lose on noise. If we go to the ultra-low power, clearly the noise flow raises up as well, and so on and so forth. So you get the idea. So for TI design, in this particular case, we're going to choose something, because we could do the 4, but for this presentation, at least for this video, we're going to be talking about 1, and we're going to be talking about a lot of details in regards to this particular design. And this one really revolves around the lowest distortion and noise at 1 megasamples per second. Okay, so we have some parameters and we have some goals to achieve. The first parameter we're going to target is the THD, all right, total harmonic distortion. We're going to try to get better than 110 dB. SNR, likewise, we're going to try to get better than 98 dB. And then for INL, excuse me, we're going to try to get, say, below 1.5 LSB, okay, which is adequate for this type of application, all right? Total power, we're going to try to keep it under 40 milliwatts. So that's the goal at least, so we'll see if we can achieve that by the end of this video. Now we move on to the next section, which really details the input driver selection and design. All right, so I say design because it really is, it's a methodology, and it's also a selection in that we get to select and choose out of several products, several amplifiers, just a handful of them. So what are some of the requirements? Well, we're trying to drive an ADC. We know that by nature this is a SAR ADC, which means we're going to run into a cap load situation, essentially, okay? So cap load is essential here, which means I'm going to need to have something that is robust enough to be able to drive a capacitor, okay? Not necessarily a heavy cap load, but certainly, say, maybe like up to 100 picofarad, up to 200 picofarad. And when you design for worst case, you ought to go to those double-digit numbers in terms of picofarads. So low distortion usually means picking a part that is high bandwidth. I'll explain that later also. Low noise also means low bandwidth. So that in there it seems a little bit counterintuitive and even contradictory. Truth is, when we talk about high bandwidth in terms of low distortion, we're talking about the intrinsic bandwidth. When we talk about the low noise and we say low bandwidth for low noise, we're really talking about externally filtering, whether it means putting a cap around the feedback, whether it means additional circuitry such as a snubber, such as an isolation resistor, and the like. So really we're talking about two different things. Keep that in mind. For the buffer, we also need low distortion. We also need low noise, clearly. We're talking about 18 bits of resolution, so we ought to keep the noise floor as low as possible. Then we talk about single supply possibly. Why? Because that's what the ADC does. The ADC operates from a single supply, 5 volt, and so we need to keep that as simple as possible rather than having external or additional components, power components that is. And then rail-to-rail output and low power if possible. Why is it important? Well, rail-to-rail, remember we're talking about low voltages, namely 5 volts and below, maybe even 3.3 volts down to 2.7, who knows? Bottom line is, if you keep it to such a low voltage, you're going to run into problems, okay? You're going to run into losing a number of codes that are never going to be digitized. Essentially, failure to digitize a number of codes out of the 4096, out of the 65,000. In this case, it's 18 bits. So you get my point. Filtering, that's just as important as the other two, meaning the robustness of the output drive and the distortion of the buffer. Filtering is important to maintain a load regulation in such a way that we limit the noise and make the op-amp stable. Okay, so filtering is not just filtering, but it's also sometimes to help the op-amp stability, okay, because we may run into issues if we're picking an op-amp that's low enough in power, chances are it will not have enough output current to drive a capacitive load, and in this case, we need to implement some kind of compensation network to circumvent that. So how do we select the buffer in such a way that we get low distortion? Okay, usually what you want to start with is pick an op-amp with much lower distortion than that of the ADC. Now, by how much, that varies from person to person, from engineer to engineer, and based on experience too. 9 dB, is it 12 dB, is it 6 dB? Again, there's really no clear rule of thumb as far as I know. However, it needs to be better than that of the ADC. In terms of speed, likewise, you pick an input driver that is much wider speed than that of the ADC. Because by the time you gain up, by the time you have maybe a multi-stage topology, you're going to lose a lot of that bandwidth, the usable bandwidth certainly. So you need to make sure to use the gain bandwidth specified in a data sheet. And then when it comes to filtering, use op-amps that have high gambit product, in other words, high usable bandwidth, which will essentially give you the low distortion, okay? And of course, again, it sounds a little bit contradictory, but it really isn't. The reason you pick a high bandwidth op-amp is to get the low distortion. You can always filter out at the end of the day to basically narrow your band and get the most out of the noise performance for a particular op-amp. We need to also keep in mind that we got to minimize the input buffer distortion, all right? Generally speaking, more often than not, you want to go with the inverting configuration, which is better for THD. Op-amps distort the output as inputs approach the limits of the input common mode range, right? Number two, inverting op-amps or configurations keep the op-amp inputs fixed at Vin equals Vin minus. In other words, Vin plus equals Vin minus, or Vp equals Vn by action of negative feedback. That equals your common mode, okay, which can be suitable if there's no common mode distortion. And it is suitable in this case because there's no modulation across the inputs. In a non-inverting configuration, though, Vn plus and Vn minus, or Vp and Vn, they'll vary with the input signal, which means you're going to get that modulation or the common mode distortion. That may affect your circuit tremendously. We move on to the input driver noise contribution. Okay, so when it comes to this, you have basically two different components here. All right, you have the noise of the op-amp, that's the voltage noise. You also have that pi over 2 factor, which is 1.57. That's the constant you ought to multiply the bandwidth by. Everything under the square root. Keep in mind this is RSS fashion, which means root sum square summation. And then you'll add to that any kind of Johnson noise, resistor noise. Clearly, that would be basically the 4kTBR. And again, multiplied by that pi over 2 factor, which is 1.57. That's for the first order filter. All right? That's what we have to talk about, the input noise contribution. So really nothing fancy here except to hand select and hand pick the proper op-amp and the choice of amplifiers very, very carefully. Okay? So once we do all of this, we actually identify, surprisingly, believe it or not, just about 4 parts. All right? So you may have been thinking, you know, when I start this process, I'm going to end up with 1,000 different devices from who knows what and who knows where. Truth is, there's only 4 different parts within TI portfolio, and that's because we're asking for too much, all right? We're asking for too much from a design perspective. What I mean is we're asking for low noise, for low power, for low distortion, for high bandwidth. So when you get all of these together, you only have so many degrees of freedom. You understand? That's really what it comes down to. That's why we come up with 4 parts. What are those 4 parts anyway? We have the THS 4031, we have the 28 OPA 2836, we have the THS 4521, and then we have the THS 4531. 21 and 31, all right? Just in case they sound alike. So they're different parts. These are mostly high-speed parts, and when I say high-speed parts, I mean something over 50 megahertz. So why are we talking about high-speed parts in the realm of precision? Well, because they do give you the precision. And that's the nice thing about these devices. They actually provide some level of precision that can achieve the performance to maintain that ENOP, to maintain the effective resolution using the ADS 8881, and certainly the speed, needless to say. So the bottom line is, out of those 4 parts, we notice the first one operates from 1.6 to 3.4. Well, we want to operate at 5 volts, remember, all right? Because the ADS 8881 does operate at 5 volts, we don't want to change any supplies, so that takes it out. We can't use it. We go on to the next one, the OPA 2836. What happens there? Well, it's nice, and it fits the bill, well, almost, except for it's a single-ended output. All right, so not yet, okay? Not quite there yet. So we got to move on to the next one, which is the THS 4521. What happens there? Fits the bill, so far so good. I look at my operating voltage. I look at my gain bandwidth, plenty enough. I look at my THD, calculated THD, fits the bill. I look at my noise, right on the money. I look at the output, fully differential. Guess what? That's what it is. That's my choice. Why? Because the ADS 8881 is also fully differential input, which tags right along. All right? So then the last one, I just throw it away, and I move on. All right, so now we move on to the low distortion anti-aliasing filter. And by filter, I really mean a passive filter that's just an RC filter, as opposed to an active filter, which would require maybe a different kind of amplifier and certainly active components. So for the time being, let's just focus on passive filtering. And again, just an RC filter. So by the time you hook up basically your driver to your SAR ADC, namely the ADS 8881, because of the topology of that SAR ADC, it has a sampling capacitor, a sample and hold capacitor. What happens is the op-amp is going to see a capacitive load. So what you're going to do is you're going to put in an RC filter in such a way that the RC serves, or the C really, serves as a charge bucket, if you will, okay? And then if you make it large enough, it can attenuate the kickback noise from that ADC, all right? Now, when I say large enough, don't make it so large as to run into problems with real estate, okay? But the bottom line is when you have that C plus the C of the sample and hold, in other words, the sampling capacitor from the SAR ADC, plus any parasitics, all of a sudden, that adds up. And when that adds up, it really creates a pole with the output impedance of the amplifier. So you're going to need an R as an isolation resistor. And by the way, that's really saying a 0 in a transfer function. Okay, so frequency response, it's going to be just an R. That's going to basically ease up a little bit on the ROC. All right, you guessed it, rate of closure. And that's going to basically make it roll off at 20 dB per decade as opposed to 40 dB per decade, which will give you problems, many problems for that matter. So pick a C that's large but not huge, not large enough. Typically keep it under a microfarad or so. Also make sure to keep it about 20 times the value of the sampling capacitor. Where do you find the sampling capacitor value? In the data sheet of the ADS 8881. In this particular case for us, it worked out to be 1.18 nanofarad. All right? So keep that in mind. Lastly, we talk about the R filter. So we talked about the C, in other words, the cap. Now we talk about the filter, or the same thing, the filter, but we're talking about the isolation resistor that goes with the C, so the RC. So we talked about the 0, and that's what this does. Usually you want to set this in such a way that this 0 comes within a decade above the pole for adequate phase margin. What's an adequate phase margin? Well, you know, contemporary designs for amplifiers, they'll give you something around 55, 60. I've seen it as good as 68, 70 degrees of phase margin. I've seen it as bad as 45 degrees of phase margin, which is kind of marginal for something like this, for a design of such precision. So bottom line is you really want to keep it at about at least 45, minimum 45, but really you should design for something around 55, maybe even 60 if you can push it up there. So that's why you need to place that 0, in other words, the R, a decade above the pole for adequate compensation or frequency compensation. All right? So that's all we have to say. Until next time, stay tuned, and we're going to be talking in more details about the input driver and a whole bunch of other stuff. Thank you for watching.